do in this hour is kind of focus in on Helix in particular and the capabilities of it and how it works together. So this is starting to get more into the details of it. And in hour 3, you're going to see how you can use this and what usability aspects we have for using it with Trevor. So just kind of going over what is the co-simulation, why are we doing it, what the philosophy of Helix was in development and how that guides how Helix works in the development and how it all ties together, and then kind of some terminology, the components in Helix, what interfaces are, how threading works, and then the time control and a few additional topics that may or may not be of interest. The idea here is to get you a background on what Helix is capable of, why it does what it does, and how it does what it does. And so if you need any of these in future work, you know it's there, and a general overview of kind of what its capabilities are should you need them in the future. Otto talked a little bit about this, but basically co-simulation, it allows the execution of multiple distinct simulations together in a coherent fashion. So if we have multiple pieces that can be simulated or executed separately, we want to run them together. So on the screen here, you see GridDyn, which is a power system simulation for transmission networks, coupled with a distribution system, coupled with a communication system. So those are the different simulators. The whole thing is referred to as a co-simulation, and what Helix does is does the coordination between them. So just some examples of this. Imagine you have a weather scenario. So it rains on a particular location with a bunch of vegetation. That is affected by kind of rain, ambient temperatures, but this also affects humidity, reflectivity, and this also has an impact on the weather. So there's kind of a feedback loop here. Same thing with on a power system side. So you have energy prices that control energy prices and voltage. That affects how much power a house use, which in turn, in the aggregate, affects how much power is consumed and how much is generated by the large transmission network and the large generators in the system. So there's a feedback loop there. And that's really the key behind co-simulation. These are very distinct components. You model them in very different ways, but there's a feedback loop between them, and you need to be able to connect them to accurately model uh, a holistic scenario, a holistic situation. It's basically a way to decouple the models, to allow them to bring them back together, and to enable consideration of effects that would not be practical to put all into a single computer simulation. When we talk about the power system, there's any number of different factors which come into play. The US energy system is a fairly complex system, probably the most complex system in existence, but there's renewable energy coming into it. It's connected between a substation and power systems and transmission lines. This is affected by the weather. It affects its transportation is coming into play. It is impacted by and impacts the natural gas system, and that's all connected via communication networks. And so when you start to consider threats or impacts to the national power system, you need to be able to consider potential aspects of all these different things. And so that gets into the multi-domain aspects of Helix and why we really wanted to do this. So co-simulation, we can couple transmission, distribution, gas, water, grid, going down into the details of a thermal plant model, how it interacts with the transmission network, electromagnetic simulation, transmission components. Basically, whenever a single simulator is insufficient to answer the relevant questions, that's when you need co-simulation. So what are the key components of co-simulation? Basically, it comes down to two very simple things. One is it's got to get the data where it needs to go, and it's got to manage who gets the data when. And co-simulation does those two things. And that's all it does. And so that seems simple on the left, but of course the key is in the details there of how that all works and what interface you use to connect all these things. For execution control, there's really two different ways of doing this. You can imagine many co-simulation frameworks use what we call a runtime manager. So this is a runtime interface, and you tie these simulators into a specific interface and allow the runtime runtime engine to execute them as you go along. So you're giving up, the federate is essentially giving up control to this runtime engine. Everything has to match up with its interface. What we chose in Helix instead was a library approach. So we basically leave the simulators in control. They can choose to connect to Helix or not. Uh, and then the Helix library only acts when the simulators tell it to act. So it's leaving the simulators in control. And we think that allows us to be able to interface a lot more easily with any number of different components to allow these simulators to execute independently or with Helix based on their choice and have the same executable run in both cases. And I'll add, if there's any questions about anything I'm talking about, feel free to speak up. And Trevor or Otto, if you're still on, if you want to watch the chat, I'm not able to see that right now. So please speak up if there's any questions I can answer along the way. The transport layer between different things, this is how data gets sent between the two. So now we're starting to get into how Helix does this. Basically, it allows data to be specified and communicated between these different federates. And so Helix uses a number of different underlying communication technologies to do this, and is quite flexible in which ones you use. This includes an in-process memory one if you are running federation or co-simulation in a single process on a computer. The TCP and ZMQ sockets are networking layers using either the TCP protocol or the 0MQ protocols under the hood. And there's two different ZMQ ones depending on the exact scenario you're using. UDP can be useful in some specific cases where you have a highly reliable network. An interprocess shared memory system when you need to transfer very large amounts of data on a single machine. And an MPI one, which can be used in high performance computing cases where you have the higher bandwidth MPI interface between them. Time coordination is basically how the execution and communication between the federates is coordinated. So that means messages need to be synchronized in how data gets sent and how time gets advanced. There's a couple different ways of doing this. One is a centralized approach where you have a single coordinator managing this. So imagine the broker in the context of Helix handling all the time coordination as well. Helix can do this, but this is not the default because it ends up being a bottleneck in the scenarios when you get to larger scales. What Helix uses by default is a distributed controller. That means each individual federate is gathering timing information from the federates it connects to directly and deciding when it can advance in time or grant time to the different federates. Helix runs in a number of different states through the system. When you first create it, it is in the created mode or a setup mode. Then it can advance to an initialization mode. The transition from the created mode to the initialization mode is the only global time synchronized event in Helix by default. So every federate needs to specify that it's ready to go into the next mode. And when every federate is ready, then the central broker grants this request and then the simulation proceeds. In the initialization mode, data is allowed to be transferred between different federates, and you can iterate in this if you need to do an iterative initialization, but time is not advancing. In execution mode, all the federates are moving forward in time between the two, and time is coordinated between them. And then there's a final mode where some cleanup can occur and some final data collection can occur as well. Time synchronization in different is handled differently in different kind of co-simulation frameworks. So you could imagine a conservative approach where federates are only granted time which is the minimum of all the different time simulators. So this is very correct and can be done reliably, but it can also be very slow if there's a lot of different points in which time can be advanced. You can imagine a fixed time step. So everybody is advancing simultaneously, but only at precise intervals. This is faster, but you have the potential of some causality errors or some messages being delayed at different amounts of times. An optimistic approach must allow rollback. So you're prospectively granting time to the different federates, and if individual federates can go back in time if something occurs out of step, this can be a significant performance benefit, but it also requires a lot of code and infrastructure in the simulators. When Helix was designed, we talked a lot about how we wanted it to work and how we wanted it to be different and distinct from existing co-simulation frameworks and what would make it meet the design requirements for it. To that end, we eventually converged on a couple different philosophical statements of how we wanted Helix to be designed. One, it has to be as easy as possible for federates to work together. So we can't make this more difficult than it really needs to be. And we want to make the APIs and the code and the structure all work together as easily as possible. Federates should not be allowed to make restrictions on other federates. So individual federates have different requirements or different designs on their own, and we want Helix to be able to work with that. And so if you want federates to work together, we can't allow Helix to enforce requirements on the other federates in the system. And federates should maintain control and autonomy. This gets back to the idea that Helix should be a library, not a runtime engine. So we wanted federates to be able to choose when they connect to Helix, to choose when they interact with it, and to be able to do other things while they're doing so. The design to be layered and modular and adaptable, this really gets into the software architecture of Helix, that it should be hierarchical, it should be layered, and the code should reflect that and be easy to maintain and adaptable to different circumstances. And then the centralized control really gets at the notion of scalability. So to minimize, we want to maximize scalability. That means we really need to minimize the bottlenecks in Helix. And so that means the design from the ground up should be decentralized. Some terminology we use in Helix pretty commonly. The federate, this is any individual executable thing that is running. We refer to cores as an object that manages one or more federates. So when a federate gets created, it often just creates a core. When the initial design, we had pictured this as being a 1 to n situation where one core could manage multiple federates. But in practice, what often happens is you end up with one core per federate. And so there's distinct kind of responsibilities in these. The core manages the actual communications and interactions with the brokers, and the federate handles the data. A broker, this is a coordinator to handle multiple cores or brokers, and there can be several layers of these. We talked about the hierarchical nature of Helix before, and so the brokers are what manage this hierarchy. And at the top of this hierarchy, there's a root broker. So this functions as a last chance router if data can't be routed through the intermediate layers, and it's responsible for determining when to enter initialization mode. And when we refer to a federation, this is all of these federates, cores, and brokers executing together to perform a single co-simulation. What you can see here is kind of a diagram of how this might work. Helix works across multiple machines. Often it can be advantageous to have a single broker per machine to handle communications inside that machine, because that communication can happen a lot faster. And so the cores and brokers will route the communications internal to themselves. And if they don't know how to get data from where it needs to be, then they'll go up to the next higher level. Any questions so far? Getting at the layered approach in Helix, there's a number of API layers internal to Helix. The first is kind of the layer 0. So this is the communications and operating system layer, where we actually deal with the code for translating the data from one communication type to another, sending the data, getting it out, deserializing it, and interacting with the operating system where needed. Built on top of this is the core layer. So this is a lot of what I've been working on inside Helix, and this is what manages how Helix works inside. And there's a core API to this, but most of what federates interact with is the application layer. And so this is where we have the different language APIs, including Python, MATLAB, C, C Sharp, Julia. This is what does the data type translation, handles some of the configuration, and basically does all the things that enable Helix to work nicely with users. Built on top of this, we have a number of apps that can be used to help build co-simulations. Um, there's a number of domain APIs, which I think Trevor will touch on in his talk. And then these kind of work with specific domains. And then above this, there's global management layers, including the Helix runner, some automation tools, scenario generation tools, and things of that nature, which operate on the global level. Otto mentioned this before, but we designed it to be two kind of distinct types of federates. They can, of course, interact together and operate in a single federate, but there's really two kind of design ideas between them. And this is to get at the notion that there are physical values that can be interacted with. So for example, a transmission and distribution coupling. Usually you would couple this sending the voltages and currents back and forth between 2 points. And these represent real physical hard connections between the boundaries of federates. These are marked by kind of continuous values. They maintain state and value, and there's only one at a time. And they can also have units and data types associated with them. Uh, in addition to that, Helix supports the notion of a packetized communication system. So these are messages that go back and forth. These are single blobs of data that get sent from one place to another. They move through the network. They can be rerouted and manipulated in process, and they arrive at their destination. And so this is distinct from the value federates. So we call these value federates and message federates. So for value-based federates, we have two interfaces. These are inputs and publications. So these are one-directional interfaces. Inputs take in data, publications send data out. And inputs can receive data from multiple publications, and publications can send data to multiple different inputs. Endpoints, in contrast, are bidirectional. So these can both send and receive data. You can specify them as unidirectional, but by default, they are bidirectional. And for inputs and publications, for any given time, there will only be one value or value set valid. For endpoints, multiple packets can be sent at the same time step or received at the same time step. Just to give you an example here, imagine we have three federates. They define some publications and subscriptions. There's a broker between them. The data goes from the publications to the inputs. When we have a endpoint, the data can go back and forth and jump around, and you can send data in different directions at different times. One of the unique features of Helix is the idea of filters. So tied in with the idea of endpoints, and endpoints send packetized data. This packetized data is going through the Helix network or some sort of network. Filters are ways to create inline operations that can alter messages or events from endpoints. So this could be time delayed. You can randomly drop them. You can clone them and send them to multiple locations. They can be rerouted. And you can do custom ones, which allows you to do whatever you want. And these are managed as part of the core. So their effect is not localized to local objects. So you can create a filter in one federate that affects messages coming or going into another federate. What this allows you to do, I'll show through an example here. So you have a transmission network and you're interacting with an AGC controller. The data is coming from the transmission network and going to the AGC controller that will do whatever processing it has to do, and then send some control signals back into the the generators on a transmission network. Well, say now you want to model the communication delay that goes into this to see if there's any effect on the controllability of the grid. This allows you, filters allow you to insert a communication delay into this. And you can do this without really changing anything on the transmission federate or the AGC controller, just by adding a filter, perhaps in a different federate or a different location. And this allows you to delay or even drop some sort of signals. Well, now say you get a little more sophisticated and you want to actually model the full communication network that goes between them. So this is where a rerouting filter comes in. So first you may need to translate the packet into a actual network format, and then reroute the message into a full communication simulation. And this is what rerouting filters allow you to do. You can take the message coming in, change its destination, but keep its original archived, go through a full communication network simulation, for example, NS3 or OMNET, and then on the other side, translate the packet back into something the AGC controller can understand and send it back to the AGC controller. And the same thing on the other path. The key feature here is that these rerouting filters allow you to inject this communication simulation independently of what you are doing to the transmission and AGC controller. So you don't need to modify those parts of the co-simulation to enable this capability. One other feature of HELICS is the translators. This is a fairly newer feature, but it allows the bridging of value and message federates. For example, a relay communication device or a data acquisition unit. So the data acquisition unit itself may be coupling directly to some sort of analog value in the power system and collecting that, packetizing it, and then sending it to some particular location to do some control action or something with this. And so these allow direct modeling of that capability, since you may not want to have a full federate that does this directly. So translators allow you to bridge the value and message federates in both directions. So messages go in, there's a two-value operation in the translator, and this can feed out to inputs. Publications go in, sending values to this, and this can go out to endpoints, collecting data. So it allows the interoperability between value and message federates in cases where that makes sense. There's some properties associated with this. There's always a small delay associated with this, as you might expect from any data acquisition unit and network device. The translator basically acts like a publication input and endpoint for purposes of connecting with other interfaces. So you don't even need to know that it is a translator when you're connecting to it from another federate. And this is convenient for the purposes of building co-simulations. There's two built-in types, including a conversion to a JSON type and a binary one, which just forwards the binary data. And then there's a custom controls, which allow a user to do just about anything they want to with respect to this. Any questions on filters and translators? Is there any questions in the chat, Trevor?
Yeah, I've been answering a few
Okay.
but yeah, we're good.
Okay, sounds good. HELICS is designed to work on a multi-threaded system. All federates, cores, and brokers are designed to be thread safe, so you can interact with them on multiple different threads. This is mainly applicable for C++ and C, although I believe Python can do some of this as well. And they can be interacted with multiple threads. So once you create them, the components themselves are thread safe. The individual objects you get by the publication subscription, publications, input, endpoints, objects, the objects you get back from them, these are not by design thread safe, although you could put these objects in different threads and these could interact with the same interface. Filters are a little more thread safe, and you can update some of the parameters in a thread safe fashion. Federates have asynchronous calls. So you can basically tell it to request time, and then on an asynchronous fashion, and then go do other things that you need to do as part of a federate and check when it's done. Although interacting with the federate while it is doing this could produce an exception in some cases. For example, if you're trying to call a time request while an existing one is in progress, this is a defined operation, but I wouldn't recommend it because it'll produce some interesting results in some cases. The purpose of this is there's probably a lot more thread safety built in than is strictly required for many of the most common use cases. And we are looking at doing a single threaded federate as well, which can have some performance improvements, particularly in some situations where you're running a large number of single threaded federates. But it is a lot easier to relax thread safety in the future than to try to add it back in later when we need it. So that is why we focused on the thread safe versions initially. What I'm going to go through now is getting progressively more into the details of how Helix works. So I'm going to kind of go through how a core actually functions. So imagine you have two federates. The federate code is doing what it does, and then it's interacting with the core API. And there's a lot of code that actually handles the core interactions here. The core interacts the core API interacts with the actual core processes through a shared memory queue. So this is a shared memory between the core API and the shared queue. The core thread basically pops the messages off this and handles them and can send data back into a queue for the individual core API, which will retrieve it upon request from the federate itself. The core thread is what is sending the data through the communications, and depending on which communication mechanism is used, there are either one or two threads used for communication, so that can be done asynchronously from the core thread itself. So the core thread will packetize the data and give it to the transmitter. The transmitter will then do whatever it needs to do to send along its selected communication path. And this is what allows the HELICS to interact with different communication mechanisms in a seamless way. And the receiver will then put messages back on the shared queue and for processing by the core thread. And so the whole cycle can keep going. So what this basically means is that in a typical federate, you will have probably four threads running simultaneously. So we recommend having at least 3 available, although 2 works. So a multi-threaded system works just fine, and it works on a single thread, but they'll be bouncing back and forth a little bit. A broker works in kind of a similar fashion. There's a user API for the broker. It puts messages on a shared queue. There's a broker thread that sends messages back. The difference here is there's only one API or user that can be allowed to interact with a single broker thread. And the same thing with the communications. It then sends messages to a transmitter and receiver and puts them back on the shared queue for processing. I mentioned this earlier, but there's a lot of scalability implications for the time coordination. So if you don't have a central controller, so what this led to is in Helix, we didn't want to have a central controller keeping the time. This is a bottleneck for large simulations, and there's been a number of studies showing this to be the case. We did some early on when we were talking about how to design Helix, and there's been a few recent test cases actually demonstrating that Helix actually achieves much more scalability than some of the other co-simulation frameworks out there. This leads to a distributed timekeeping. So time advancement must be distributed and controlled locally. This probably means the timekeeping in Helix is a little more complex than a centralized controller would be, but it has the advantage of being scalable. It also leads to a hierarchical design. So interprocess communication must also be distributed. So there's no central place in Helix that keeps all the time, that keeps all the data is routing through, which makes debugging a little more challenging, but it also preserves the scalability aspects of Helix. Helix goes to the extreme in this case, that every federate has an independent time control that is responsible for its own timekeeping. And so this means that parameters and controls can be updated on the fly. These controls don't need to be transmitted to other federates, and this gives us a lot of flexibility in how individual federates control their own time and how they integrate with others. And this gets back to wanting it to make it as easy as possible for new federates to connect. So federates have different time notions of time inside them, different steps or different ways they advance in time. And we want the flexibility in Helix to be able to handle and integrate them all together. How it works is you have an individual federate. So there's incoming data of either messages or values. Helix has a specified delay that gets added to the time of these messages before it actually gets to the federate, and the same thing on the output. So there's an extra delay that can be added. In many cases, these are just zeros, but depending on the circumstance, you may want to add specific delays to the input and output for these to mimic specific circumstances or um, specific controls on a federate. Helix supports the notion of time periodicity. So often in power system simulations, these only execute at specific periods. That's controllable. And so Helix allows the specification of a period of operation and an offset on which can shift these. There's also a notion of a delay that you don't want a federate to execute so often. So as you can see here, a federate may then only be granted times, so integer periods plus the offset. And how this works inside Helix is if it gets a event or message at times in between these, they are delayed until the next grantable time. The time delta limits how closely two grant intervals on Helix can be. So two granted intervals may not be closer than the time delta, but this still allows iteration. We get to that. So if you want to execute multiple times at the same time step, this does not interact with that. But this kind of couples closely with the period, and you can be used to achieve some different intervals. The minimum time clock resolution on Helix is 1 nanosecond. This is a compile time setting. So if you really needed lower time intervals, you can compile Helix with a different clock resolution. So in summary, there is a federate info object that is usually created before a federate gets created and it's passed in. And this you can specify a number of different parameters on it, including input, output delay, period, offset, and time delta. And these properties can also be set dynamically as a federate is going on. A number of other flags kind of control how federates interact with each other. The observer flag specifies that a federate is receive only, so it doesn't publish data. So that means its time advancement does not impact anybody else's, and is source only, indicating that the federate does not receive any data, which means it's not impacted by anybody else either. Uninterruptible means that time cannot be interrupted. So what happens when you create a time request, you request a specific time associated with that. And this can be farther in the future than the next allowable interval. But what Helix will do is interrupt that time and grant a time earlier than requested because it has new data available to a federate. And now if you specify the uninterruptible flag, it will not do that. It'll just wait till the time you requested. The only update on change and only transmit on change means that values will not be transmitted or will only be received if the data is actually changing. So if duplicate data is sent or received, it won't indicate that there's an update. And then the wait for current time update flag indicates that a federate should be delayed until all the others have passed the requested time before granting. So this is useful in cases where you have a few stages that you want to execute and you want to specify that this particular federate should get values from the current time. Uh, any questions on the time control in Helix? Still good on the chat, Trevor?
Yes, we're good.
All right. Queries are basically an asynchronous question asking mechanism. So you can see the page there, it's on the user guide as well. But a query is a way to get information from Helix about a particular federate or about the co-simulation as a whole. The response to this is usually just a single string. So you specify a target, which is the location in Helix where you want to go, where you want to ask the question of, and then the response is usually a JSON string. Mostly, there's a few exceptions to this, but it's mostly responding in a JSON string with the information you requested. This allows you to kind of get information about the co-simulation as a whole. For example, you can get information on what publications are available, what endpoints are available, what federates are connected already, what the state of those federates is, and other things about how things are going or information about a particular federate. And there is a callback mechanism that allows federates to specify additional answers to particular queries. So if you know of this, you can ask questions about that query, about that federate, and get some information. So this is quite useful for setting up a co-simulation and for debugging a co-simulation. So in some cases, you have a federate, it may not know what it needs to connect to initially, but it knows it needs to connect to everything published by a particular federate. So you can use a query to wait till it's entered initialization mode, so it knows it's published everything it's going to get all the interfaces to this federate, and then to create the appropriate connections to that federate. And this can all be done inside Helix. They work. Basically, you make a query through the API. The local federate tries to answer the question. If it doesn't know, sends it on to the core. If the core knows, answers the question, returns it back to the location who asked for it. And that's a blocking call. So it'll block until it receives the answer. If the core doesn't know, sends it on to the broker. The broker tries to figure it out. It either generates the answer or figures out who knows the answer, and then it will either send it on down to the appropriate entity inside Helix or answer the question and get it back. There are queries in Helix which require asking questions of everybody in the entire system. These are somewhat time consuming, but they are very useful for debugging or other conditions where you want to know the entire state of a co-simulation. Targets for this can be core, broker, root, or federation. These are globally recognized targets. You can also name specific items inside each of these. So all the objects in a federation have particular names associated with them. All the federates have a given name from the user who created them. The core name will either be automatically generated or specified by the user, and likewise for the broker name as well. Commands are pretty similar to queries in that they're an asynchronous communication mechanism, but they are allowed to request actions from another federate or broker. So you're basically sending a command and a target, which is pretty similar to queries. There's a few built-in commands which allow you to remote terminate or query the logs from a particular federate. This is quite useful for debugging when you're on a multiple system and you want all the logs for the co-simulation to go to a single location for debugging purposes or other spawns, or for some reason you need to kill a federate that's acting badly, and so this allows you to do that remotely. And federates can define and respond to other federate-specific commands. There's also some commands that are useful for debugging or halting the time inside a co-simulation. And the complete list of available commands are specified in that link there, which is part of the user guide. Helix is able to iterate during the initialization or during a time step. So this allows you to send data back and forth multiple times to converge to a single value or to handle kind of multi-stage communication that happens on a single time step for simulation purposes. Internally, the way this works, it's basically Helix asking a question: is there new data, and is the iteration below the maximum iteration limit? That is all Helix is doing at the core level. The notion of convergence is left to higher levels. So at the application API, you have the notion of values within a certain delta are not sent on, which means there's no new data. So for example, if you wanted your tolerance level to be 0.01, you can specify a minimum threshold in the application API that it will not transmit any data that is that close to the previous data. And so that is a way to manage kind of tree-like convergence inside Helix directly. There has been some work on higher level notions of convergence where multiple federates are involved and doing some numerical analysis on that, but I'm not going to cover that anymore here. There's also a notion of iteration during startup to allow kind of phased creation of a co-simulation, and this is a more recent advancement in Helix. Basically allows you to specify that you're done for now with the creation, but you may have more to do later based on what everybody else does. And so once the root broker receives this, it still waits for everybody to request initialization, and then everybody who requested iteration is then sent back into the created mode to do it again. Configuration in Helix is managed through configuration files or through the API or some on the command line. These are specified in JSON or TOML. And then Trevor has created a large interface configuration list of all the possible connections between them. Connections between the interfaces can be made remotely. They do not need to be made on the federate making the connections. The idea behind this was something like an FMI module, which basically defines all its inputs and outputs, but it doesn't define anything with the connections. And so you can create multiple federates based on these and then create the connections in a different location, either through the broker or a different core. Just kind of going through a rapid list of the other features in Helix. Helix can generate profiling data. This is useful for determining kind of where the time is being spent in a co-simulation. It basically triggers a profiling message whenever Helix enters and exits into one of the Helix blocking calls. Logging is supported through consoles, files, or remote logging. There's a notion of tags, which is basically metadata, and these can be added to interfaces, federates, or cores, and these are queryable and basically allows individual interfaces or federates to specify some additional information about the particular interface they are working with or how their federate works. There's a mechanism for blocking time. So this allows you to do debugging. Say you wanted a federate to advance to a particular time when something interesting may occur that you're trying to figure out what is going on. You can tell it to stop before that time and then progress through it. And this really facilitates debugging. Sometimes federates really are just doing simple things that are responding to particular events, in which case this is can be manipulated through what we call a callback federate. And so there's a number of different callbacks that occur at different particular events inside Helix and can be run as part of the core thread. Adel mentioned units, but Helix has a full units library built in that can convert basically pretty much any unit you can think of and manage them more directly. All the fundamental data types, so this includes vectors, strings, doubles, a named point, which is a string plus a double, complex numbers. These can all be converted in some fashion to each other. Some are lossy, though. There's a number of included applications. This includes a player, which basically sends out data, a recorder, which captures data, and clone, which basically uh, can duplicate all the data going into and out of and all the interfaces of a particular federate. So useful for creating kind of templates or dummy versions of co-simulation where you're doing testing. A recent advancement in Helix is the ability to do dynamic federations. This includes dynamic subscriptions. This has been in a while. Observers, which are basically federates that can join at any particular time that can capture particular values of a federate or the federation. Then dynamic publications and endpoints allows the creation of new publications as time goes along. From existing federates, and then the last stage was a full dynamic federation. Trevor has had some suggestions that this is really useful for debugging as you're slowly building up a co-simulation and doing dynamically building for testing, and particularly in combination with the time barriers, which do the blocking operations. Couple things we're working on it. We've narrowed down this list considerably in the recent years, but a couple of things we're tinkering with yet are single thread and single federate optimized cores. So a lot of I mentioned earlier that the federates and cores are built to be thread safe, but there's a lot of cases where there's a 1-to-1 ratio between them, and you don't really need to handle the different threads between them, and that is actually consuming additional resources that are somewhat unneeded. And so having a single thread, single federate optimized core for this can reduce the thread count and reduce the amount of resources required to run a federation, and allows you to put more federates on a single machine if that is desired. And then the idea of a partitioned federation, which basically restricts the visibility of particular interfaces to different sublayers. So if you have a hierarchical system with multiple brokers that are interacting together, maybe there's only a little bit of data that you need visible between these different co-simulations. So this kind of is something we've been tinkering with a little bit to handle very large scale co-simulations and scalability. I'll end with this comment. Helix was built to be able to allow different federates to work together, different domains to work together to solve problems which cannot be handled together. And we think this tagline for Helix really captures that simulations are better together. And Helix was built with the partnership between a number of different national labs. And I think the software that came out of it is an embodiment of that collaboration between ourselves. So that was kind of a rapid fire deep dive into how Helix works and what's going on behind the hood when you build a Helix co-simulation, and a little bit of the philosophy behind the design of it. Happy to answer any questions and any discussion points you want to bring up. Anything more in the chat, Trevor?
Nope, nothing more right now.
All right.
Well, let's
And
take another 5-minute break. We can stop at the top of the hour, and we'll get into the last section here for today.